Hey everyone, and welcome to our webinar presentation. My name is Adam Harris, CEO for C-Therm Technologies. Really excited to welcome you today to our application feature presentation on looking at using thermal conductivity data to build better geothermal modeling. We have a special guest speaker, Joseph DeLuca from the University of New Brunswick's Department of Earth Sciences. Joseph is a researcher up at UNB that's working on improving the modeling and mapping data for optimization of the geothermal placement and improving overall efficiency with geothermal. This is an exciting area of application which C-Therm has considerable history with. We've worked with a number of researchers around the world on improving geothermal mapping data. I see some of those researchers online with us today from Italy, from throughout Europe and the US. So great to have you online with us. C-Therm, one of the things we've done since the start of the pandemic is we've really upped our game in terms of producing educational content featured around application areas of thermal conductivity. So what we try to do is illuminate an area where thermal conductivity is of significant interest. We try to explain why the thermal conductivity data is important and how best to navigate the method selection and approaching how best to measure the thermal conductivity of these types of samples. And wherever possible, we like to get guests in on the discussion. I'm really pleased today to have Joseph with us here. He's been doing some interesting work that was initiated by a C-Therm researcher, Dr. Robert Bateman, in collaboration with the Department of Earth Science up at UNB, and this is some of the resulting work that Joseph has led from that collaboration. So it should be an exciting review of where thermal conductivity data is applied and why it's important in this type of application. I'm going to be leaning on a subject matter expert from C-Therm, Arya Hakimian, as well. If you've participated in a number of our webinars, you're familiar with Arya's work and thought leadership in measuring thermal conductivity. He's going to help me provide a little bit of an introduction to the TPS method, which is featured in Joseph's research, and explaining a little bit the theory of operation to it. Just before I introduce Arya, I'll provide a little bit of background on who C-Therm Technologies is. I see a few new names and folks that maybe aren't as familiar with us as an organization and the technology we offer for this type of characterization work. So I will provide a little bit of a primer on that before transitioning to Arya, and then the star of our show today will be Joseph. So first off, who is C-Therm Technologies? A little bit of background on us as an organization. We're a Canadian tech company based on the East Coast in Fredericton, New Brunswick. Our purpose for being, our raison d'etre in life, is all about simplifying thermal conductivity testing, largely for the materials of tomorrow. So we work a lot with groups that are developing new composite materials, novel materials, or advancing a science around harnessing thermal conductivity. In the case of geothermal, it's a great potential and already widely in use as a very energy efficient way of heating and cooling some of our climates within our buildings and houses and so forth. Our goal is to really simplify the process of generating accurate representative test data. So not just being able to measure thermal conductivity easily, but be able to measure it under truly representative conditions. In some of the work in geothermal, for example, we won't be getting into it as much in today's presentation. It's important to measure at very high temperatures and high pressures. C-Therm has advanced some new technological capabilities for high pressure, high temperature measurement. The new TLS HT300 is an example of that, which allows testing of saturated pressurized samples up at very high temperatures and pressures, 300 degrees C and I think 3000 PSI. Igor, if you're able to easily locate it, perhaps a link to that launch webinar might be an additional resource we want to provide the audience, if you can drop that in the chat box. Our core product line, we're going to focus today really on the one on the left. It's a low-cost kind of entry-level system, kind of gets you in the game, so to speak, of measuring thermal conductivity. It's a thermal conductivity kit developed by C-Therm. It includes a transient plane source sensor, which we'll describe a little bit more detail with ARIA section, a reference material, the data acquisition software and regression analysis software, as well as the standard connection, which would connect to a Keithley source measure unit. So with the TC kit, Keithley is used as the data acquisition system, and it integrates with the C-Therm provided software, and this makes for a very basic capability to measure conductivity. It works very well for solids, and particularly the solids like we're going to be testing in terms of geological samples. So we'll feature some of this in today's presentation. Now, this does not, it's consistent with the principles of the ISO standard 22007-2, but it doesn't fully meet the standards of that require a bridge circuit design that enhances the dynamic range and sensitivity of the data acquisition system. So that's available on the Trident platform, and that's really the one you see in the middle. That's our core product. Was launched a couple of years ago to great fanfare. It brings together three of the most prominent methods for transient thermal conductivity, including the patented MTPS method, which is a single-sided technique. Also great for solids, liquids, powders, pastes. Probably the simplest of the three to use would be the MTPS. The one in the middle is the transient line source. This is used a lot in geological research and does offer some higher temperature, higher pressure capabilities, as I noted, up to 300 degrees C. And then the Flex TPS, of course. And on Trident, we have this available at a wider temperature range and broader dynamic range of measurement for thermal conductivity. I won't talk much about the one on the right. This is really more for consumer goods, textiles, and so forth. It relates to quantifying and measuring touch properties, such as the warm feel or cool touch of materials. That closely relates to a associated thermophysical property we measure called thermal effusivity. It's a bit off topic for today, but if you are for some reason interested in quantifying touch, we have a wealth of resources we can share with you on some of that work. Okay, so just a little bit more detail on Trident, is it will be of interest to a number of folks in the audience. So with Trident, it's all about bringing those three most powerful transient methods for thermal conductivity together under one platform. So you have the Flex TPS, which we'll be featuring in today's work, the needle probe, and the MTPS. The important point I just want to share here with you is that when it comes to thermal conductivity, it really is better to take more of a toolbox approach. There is no single method that really handles the full range of scenarios, of materials, atmospheric conditions, which a person may want to test for thermal conductivity. So I really like this quote from Abraham Maslow, which captures the value proposition to Trident nicely, is that when all you have is a hammer, everything looks like a nail. And so this is where the most common mistakes are made in measuring thermal conductivity in industry and academia, is applying the wrong tool for the job. And so it's really important to understand what's the right tool for the job at hand. We do have a nice method selection guide available. It's been co-authored with researchers at C-Therm and external subject matter experts. It's a comprehensive guide meant to inform on which application areas should be which methods should be applied for different application areas. So this covers both traditional steady state techniques like guided hot plate heat flow meters and all the transient methods that are significant, including techniques such as laser flash. It's a great free resource available for download. I think if Igor hasn't already, he'll be dropping in a link to where you can download that from our site. Encourage you to check it out. It does do a really good job of informing the appropriate method selection for different types of materials. Now, today we're going to be really focusing on the kit and what that looks like. This is what's been used in the data acquisition, and we'll be talking more about that as I transition this to ARIA. I did just want to leave you with a nice client testimonial, a couple of them. This one is from a researcher at the Ryerson University here in Canada. Dr. Kandakar Hossain. Dr. Hussain comments, the thermal conductivity measuring device, the TC kit, is easy to operate. A new user would not face difficulty in using it. The kit can also provide test results within minutes. The nickel sensor is flexible to use. Moreover, it is suitable for testing cement-based composites and geopolymer, which is very important for our research group. As a whole, the TC kit is a useful device to investigate the thermal behavior of solid material. This equipment is a great addition to our research lab and will allow us to operate to open a new area of research. That's a good reference from the academic sector. This one's from an organization be easily recognized by everyone here. NASA, nice comment from Dr. Enrique Jackson, just commenting on the purchase of a C-Therm system after seeing a demonstration of how fast and easy it is to operate. The instrument provides us unequivocal results and provides the flexibility to test powders and liquids. In terms of our satisfaction with the purchase, I'd give it a 10 out of 10, extremely satisfied. It's Dr. Enrique Jackson from NASA. So just a couple of testimonials. If you'd like to get more exposure to what our clients are saying about their experience in working with C-Therm for thermal conductivity, I see that Igor has dropped in the link to the chat box. There's, I think, 50 or 60 of these testimonials available online. You're certainly welcome to scroll through them. We try to identify what kind of application area they're in so you can better understand if it matches up well with the type of research you might be conducting. We're also happy to introduce you to any researchers that we have in the field. So if you would like to talk to somebody, we can certainly provide some introductions that way as well. I see Arya has joined me on screen. Really happy to welcome Arya to the discussion. Arya is a subject matter expert, application scientist here at C-Therm Technologies. He runs our demo facility, helps clients understand the capabilities and limitations of the different methods. He's a scientist and very good at helping coach folks in terms of appropriate method selection and brings a wealth of experience in this capacity to the discussion. So really happy to have Arya join us. He's going to walk us through a little bit of information in more detail on how the TPS method works. And we'll introduce Joseph, which is the main act to our show, who will be taking us through more of the application data. So at this point, Arya, I'll pass it over to you, and I'll rejoin you at the end of the presentation. Thank you.
Awesome. Thanks, Adam. Hello, everyone. So as was mentioned, just going to do a little overview on the TPS method at a high level to kind of set up some of the background information for what Joseph will be presenting with some of the content in his section. So at a high level, the TPS sensor, transient plane source, it's a double-sided sensor design. This means that you do need to have a sample on the top and bottom side of the sensor to perform your measurement. It does provide you with a lot of flexibility over your experimental design, specifically looking at adjusting the timing and power settings for your measurement. With the TPS, there's no contact agent required. Certain methods will require the use of a interfacial material or agent between the sensor and sample. With the TPS, this is not required, making it a really great option for materials that may be hygroscopic in nature, would react with a contact agent, or perhaps if they're extremely porous. Highlighting that the TPS in general is recommended for more advanced users. It does require a little bit more understanding of the method on how to properly set up and operate the instrument, analyzing the data, things like this. All your measurements that are taken on TPS, you will go through a verification process, which is done in accordance to the ISO 22007-2 standard. Again, of course, looking at the TC kit, there will be some slight differences in conformity based on the TC kit TPS versus the Trident TPS, which was briefly illustrated in that opening video. But again, the way you go about verifying and validating your results will be quite similar. So at a high level, principles of operation for the TPS, again, it's a double-sided sensor. So main idea with your setup is you're going to have a sample on the top and bottom side. that heat pulse that's delivered from your measurement will be radiating out in all directions within that material. You as a user will require to adjust the timing and power parameters for your measurement. As the measurement is running, you'll see that the data that we're collecting is looking at the change in temperature that occurs as a function of time. This will be fairly consistent across any transient-based measurement. Again, here true for the TPS. And the big thing with TPS at the end is there is this verification process that must be followed. So again, there's a lot of guidance provided in the ISO standard on how to go about doing this and why it's important in order to getting those good, accurate, reproducible results. So I'll kind of just touch on this very briefly, but the verification process essentially involves taking a look at about 6 or 7 checks that need to be met. You can see those listed on the left, things like the total temperature change in the sample. There are some calculations that need to be done, such as the probing depth, things like this. Now, of course, this process is very, I'll say, systematic in its approach. You can see the flow style chart on the right. There will be steps that you will take. You go check by check. If it passes, you move on to the next, so on and so forth. However, if at any point along the way during your process there is a failure that is met or something doesn't meet the minimum criteria or the requirement, there may be an adjustment that you can make, perhaps looking at different regions of data. Other times you may have to rerun the measurement with a different set of parameters, but ultimately you'll go through this process from the very beginning all the way to the end in order to validate your measurements according, again, to that ISO standard. One example I'll just give you is on the probing depth check. This is one I like to kind of highlight because it's pretty easy to visualize here. But you could see in this example, you could set up one material but run it with 3 different sets of test parameters, and they may not all yield valid results. So in the example on the far left, looking at a very short test time, the heat pulse that's generated may not be strong enough or significant enough to penetrate deep into that material. There is a minimum depth that needs to be met for the TPS measurement to be considered valid. And of course, in this case, it is not. So this would be an example of an invalid measurement. On the far right, though, we see essentially the opposite case scenario. Perhaps you've run the measurement for too long, or maybe too high of a power level. That heat pulse is oversaturating the material it's penetrating through, perhaps hitting a boundary condition. These would also be things that would result in an invalid measurement. And again, this is something that you would want to avoid. Leaning in the middle there, this is why using these checks, you can hone in on the proper set of conditions that in this instance give you enough material analyzed without over penetrating and oversaturating your run. So just kind of a very kind of basic example there on why these test checks are important and how they need to be done for your TPS measurements. So all that being said, I'd like to pass it now to Joseph DeLuca, researcher from UNB, to take us through some of the work that he has been doing with these geological samples using the TPS method on Trident. So I'll go ahead and stop sharing there and pass it over to you there.
Oops. Sorry, 1 second. Didn't realize it would open on that slide. Yes, so hello. My name is Joseph DeLuca. I am a 3rd-year undergraduate student at the University of New Brunswick in the Department of Earth Sciences. During the summer of 2021, my supervising professor and I worked on what started as a 4-month research project examining New Brunswick's geothermal potential. And so now the project has expanded into a 2nd phase. And so today I'll be sharing the results of phase 1 and some details regarding the new expanded research that is taking place this winter. Whoops. Okay. And here's the outline of what I will speak about today. And I want to start by first introducing the concept of geothermal energy, which is really an umbrella term for a collection of renewable energy production systems and techniques that use Earth's internal heat and the natural flow of heat in the Earth to produce clean electricity. Although geothermal energy is classified by the Government of Canada as an emerging technology, it has been in use at the industrial scale for over 100 years and is currently used in more than 27 countries. Earth's internal heat comes from two main sources, being heat converted from the planet's energy of formation and radiogenic heat, which is caused by decaying radioactive isotopes in the upper crust. The Earth is much hotter at the core than at the surface, and this temperature difference drives what's called the geothermal gradient, and that is the amount by which the temperature increases as you move from the surface inwards. There are numerous smaller, more localized processes that produce and move heat in the Earth, such as volcanic activity, but these are not relevant to New Brunswick. The focus for New Brunswick's, it's skipping 2 slides at a time, I apologize. The focus for New Brunswick's geothermal potential continues to be in decay heat from radioactive isotopes and any potentially elevated heat flows through moderate temperature sedimentary basins. So geothermal energy can technically be developed anywhere, but in order to be economical, you need sufficient heat at shallow enough depths to minimize costs associated with geothermal development. So this means you need high geothermal gradients. Which brings us to the purpose of this inquiry, which in the simplest terms was meant to determine geothermal gradients throughout as much of New Brunswick as possible. And there has been some previous discussion on this topic. For example, this map furthest on the left is one of the earliest geothermal potential maps to include the province of New Brunswick, and it was published in 2004 by the American Association of Petroleum Geologists. The entirety of this map is an inference based on 11 sample sites referenced from a 1995 map that was developed by these same authors. And this map in the middle was published in 2011 and referenced as a source for New Brunswick, the 2004 map, except it only took 5 sample sites, and those are those triangles. And on the right is a map published in 2016 by the Canadian Geothermal Energy Association and Natural Resources Canada, and it used as a source the 2011 map. So all 3 maps agree that there are elevated temperatures in southern New Brunswick, but with so few survey points being continuously recycled without too much new information added since 1995, we haven't gotten over time any better of an idea about the nature of this heat and where exactly is its origin point. We were aware of many more documented sample sites that were worth examining that just hadn't been aggregated into one report. And so this is what we did for our update on New Brunswick's geothermal potential. We made new geothermal maps and databases, which included all viable points that we could gather. And our methods for this update are best divided into 2 parts. The first being an examination of 792 archived well reports, which mainly came out of the oil and gas industry, but many came from other industries as well, such as the potash mining industry. These records span the date between 1909 and 2011, and just for fun, this is on the slide is a clipping from a 1909 well report. It's the first and last page. So we summarized all of these reports into one data bank, which we made in Excel, and in that data bank includes information for each well, such as its identifying number, where exactly is it located, its drill depth, whether the well was deviated, and other information. And so once we had a complete data bank, we calculated geothermal gradients by taking the measured bottom hole temperature that was listed in the reports, subtracting an average surface temperature of 5.5 degrees Celsius, and dividing that number by the given or calculated vertical depth of the well. And then we multiplied all of our results by 1,000 so that we could get values that were in the units degrees Celsius per kilometer. So this is our average increase in temperature per kilometer depth. The limited amount of information provided in most of the drilling records meant we were only able to calculate average thermal gradients for 106 of the 792 wells. But we took these 106 points plus 10 others that we took from other studies, and used Surfer, which is a map-making software, to produce a variety of geothermal contour maps for New Brunswick. And when we looked at these maps, we recognized there were some areas of interest where there were elevated temperatures, just as the 3 maps we looked at described that were in southern New Brunswick. So with that, we moved on to obtain thermal conductivities of rock core taken from southern New Brunswick. And later, I'm going to briefly talk about why thermal conductivity is especially important for the second phase of this research project. But for now, I'll just say in general, the reason thermal conductivity is so important is because embedded into it are a variety of factors that describe rocks, such as their mineralogies, their densities, their fluid saturation levels, and other factors. And when it comes to understanding geothermal regimes in a given area, it is important to know what rocks you have and what are their thermal conductivities. There are a lot of already published thermal conductivity measurements for all different rock types. However, there is a lack of thermal conductivity data specifically on New Brunswick rocks. And so for thermal conductivity, I like to give the example of a boiling pot of water on the stove. The metal pot heats up faster than the water, but it cools down faster as well. And this is because, it cools down faster as well, while the water itself retains its heat much longer. And this is because the water has a lower thermal conductivity than the metal pot. So the geologic analog is that rocks with high thermal conductivity absorb surrounding heat very easily. But if they're not properly insulated by low thermal conductivity rocks, they can release their heat just as easily. So rocks with very low thermal conductivities act as good heat insulators. And where you have good heat insulation, colder measured subsurface temperatures are not necessarily negative indicators for high geothermal gradients and thus good geothermal production potential. On the other hand, rocks with very high thermal conductivities can sometimes produce what is called the heat chimney effect, where they draw up any available heat from their surroundings and funnel it upwards. And the heat chimney itself is thought to be an excellent indicator for geothermal potential in a given area. So with our time available during the summer, we were able to test 41 rock cores, which represented 9 different rock types. And we got these cores from the Fredericton Core Archived and used a TC kit that was provided by C-Therm to do the physical testing. So I have a picture here. We used a 13 millimeter double-sided sensor sandwiched between 2 slices of prepared rock core. And prepared in this case just means we cut the rock core in half and polished the inner surfaces so that we could have a very smooth contact with the sensor. The TC kit came with a piece of software for interacting with the equipment, where you could set the amount of power to the sensor and for whatever length of time. And what gets measured is how hot the rock gets in response and to what depth the heat penetrates the sample. Our cores were all tested at standard temperature and pressure on a flat tabletop while they were fully dry. But later we did take several of the cores submerged in water for a week and retested them with the same setup to see if the results were any different. We used a plastic box over the setup to reduce external vibrations, although that ended up not being very much of a problem. And we accounted for rock heterogeneity by retesting each core 4 or 8 times, depending on whether the core had been cut in half or into thirds. So before talking about results, I will briefly state the main limitations of the study, and that was challenging well reports and lack of time. So first of all, the well reports were not uniform. They varied a lot in the quantity and the reliability of the information they provided. Some information we could have used to calculate thermal correction factors like geologic structures in the subsurface, and especially time between the end of drilling and when the bottom hole temperature was tested, were not present in most of the reports. And again, this inquiry was limited to the summer months, and the vast majority of our time was spent aggregating well report data. With the time limitations we had, we were not able to take into account parameters such as mineral composition, exact porosity and density, and other factors of the cores into our testing model. So keeping these limitations in mind, here are the results of part 1. On the right is the geothermal contour map in color. It is generated using our 106 points plus 10 others from previous papers, which I've listed below the map. The map itself is laid over GeoNB's official bedrock geology map of the province. We varied some aspects of the contour map to see how it changed. For example, when we excluded wells that were shorter than 500 vertical meters or 1,000 vertical meters, And the purpose of this was to see whether seasonal surface temperatures would be affecting geothermal gradients through the columns. We don't have a lot of time to look at the other maps, but suffice to say that regardless of what we did, we came up with basically the same picture every time and the same areas of interest of slightly higher thermal gradients that are concentrated around known subsurface salt bodies. Something I want to point out before I move on from this slide is these two areas, these two kind of general areas at the bottom of the map with elevated thermal gradients that are not connected in the middle. There's a colder area between them, and I'll talk about that again in a couple slides. And here's a contour map generated using the same 116 points, except now it demonstrates the amount of drilling required to achieve at least 80 degrees Celsius subsurface temperatures. So that is the currently accepted minimum temperature for what's called low temperature or low efficiency geothermal production. And then next is the results of the thermal conductivity testing. We charted all of our measurements into one table, but the entire table is too long to put on a slide. So at the top is just a clipping from the table as an example of what it looks like. And this table to the right is our calculated averages for each of our 9 rock types in watts per meter Kelvin. We're going to look at the table as a series of bar charts instead because it helps to demonstrate our calculated thermal conductivity values are mainly aligned with what has already been published. But just to note in advance, I do have to skip a few rock types for time. So at the bottom of all of the charts, labeled measured, is going to be our results, and above that is going to be those collected from other published papers. So these are our 2 igneous cores, basalt and granite. Our basalt measurements are higher than the 3 other result sets collected at the time. And although this could be due to something significant, it could simply be caused by a lack of comparative information. For example, we started with the granites as having lower thermal conductivity values than the 1 other paper we had collected at the time, the Grasby paper in the middle. But when we found a second paper, it now appears our measurements match up with previous lowest recorded values. So it could be the case for both these cores that we simply don't have enough comparative data, or these thermal conductivity measurements are being influenced by factors we didn't have time to control for, such as core mineralogy. And here's what the tables look like when you have a lot of comparative data. These are our water and air saturated sandstones, and our results are supported by these other authors that we collected. And if you're wondering about the variability of results between papers, the rocks that are used in these studies, of course, came from different parts of the world, and every author used a different technique for calculating thermal conductivities for their cores. So we use the C-Therm TC kit. We can still make reasonable comparisons by looking at general trends. And what's really significant is our evaporite results. And as supported by other papers, our evaporites had the highest thermal conductivities of all 9 rock types that we tested. Even at the lowest end of the measurement range, each of our evaporite cores tested with thermal conductivities greater than 4 watts per meter Kelvin. So the results of the thermal conductivity testing lend some, at least preliminary, support to what we saw in the contour maps, that there are areas of higher temperatures, higher thermal gradients surrounding where there are evaporitic bodies in the subsurface. And this 2017 study offers further support to this. They stated that rocks reflecting the best potential for geothermal production have thermal conductivity measurements above 4 watts per meter Kelvin. And there are a lot of studies. Oop. Has it gone to the next slide? Here we go. There are a lot of studies that have already been published describing how evaporitic bodies and their very high thermal conductivities are good indicators for geothermal production potential, such as the study at the top. And I mentioned before that the heat chimney effect, which is described in this lower paper and many others, some authors have suggested that salt's uniquely intense heat chimney, I should say, make them particularly suited for geothermal production. So what does this mean for New Brunswick specifically? A report published by NB Power in 2017 and another by the University of Alberta in 2018 both suggested that reaching minimum temperatures necessary for geothermal production in New Brunswick would require an average amount of drilling that is not economically feasible for the province. And these are the figures up here. And just to put them into context, on the left is a photo from the Iceland Deep Drilling Project 2, which is part of a volcanic industrial geothermal production system in Iceland. It's drilled to a depth of just over 4.6 kilometers and reaches a bottom hole temperature, or reservoir temperature, I should say, of over 420 degrees Celsius. On the right is a sedimentary geothermal production well, which recently completed drilling in Saskatchewan with a terminal depth of 3.5 kilometers. I'm not immediately familiar with the detailed thermal data from this well, but it is already in use and it's already producing power. So if you read either the New Brunswick Power Report or the University of Alberta report, which even specifically states that New Brunswick is not considered to have significant potential for geothermal electricity, you're likely to conclude that geothermal energy in New Brunswick is not economically feasible. But with current trends in low temperature geothermal development technologies, producing geothermal energy has become possible at far lower temperatures than what these two reports once suggested. In our inquiry, we found that in certain areas of the province around the subsurface evaporites, geothermal gradients may achieve these reduced minimum temperatures in less than half the amount of drilling suggested by the two older reports. Furthermore, the 2017 New Brunswick Power Report specifically discussed New Brunswick's potential for what's known as enhanced geothermal production, which is one technique used when hydrothermal resources are not natively present in the subsurface. Water is pumped down into the ground where it can collect heat from hot, dry rocks at depth, and then it is brought back up to the surface for use in electricity production. And in 2017, the town of Sussex, here in New Brunswick, commissioned a feasibility report on using the water that had flooded their decommissioned potash mine for use in geothermal production. Last I read, the report is still in phase 1, but they were able to actually come up with a dollar figure for such a project. And projects such as geothermal development can be of economic benefit across the board. The sedimentary basin geothermal well in Saskatchewan cited knowledge that was stored in the blue-collar oil and gas workforce as being one of the main reasons their drilling project was so successful. And it proves the economic question about geothermal energy is really more than just about reducing drilling costs down to the smallest possible number. So everything sounds good for now. However, there is still a need for further learning on this matter. On the right is a rendering of Nova Scotia with some of their calculated geothermal gradients as these little colored dots. So these authors did not infer a province-wide map by connecting their data points, so ignore the block colors in the background. We can see where this yellow arrow is pointing. One survey point which has about a medium thermal gradient has right next to it another survey point with a much lower thermal gradient. And whether this is due to insulating layers in the subsurface or mineralogy or water saturation levels or something else, we don't know yet. But it is important to notice because we do see the same thing on our map here with the yellow arrow as well. So in summary, our findings are mostly aligned with previous studies on New Brunswick's geothermal potential. However, our update does show areas of interest specifically concentrated around known subsurface evaporitic bodies. So this alone has potential for further studies. Our study could also not account for a lot of physical and chemical nuances regarding rock thermal conductivity because of time. So again, this is an area for potential further studies. And overall, one of the main challenges with nationwide potential renewable energy studies is that there are just too many records to sift through, and attention is always focused on the areas where we know we have the best potential for alternative energy. So in Canada, that would be New Brunswick. That would be British Columbia tends to get the most attention in these nationwide maps. What we noticed in our study compared to these nationwide studies on geothermal potential is that these more narrow examinations can yield these greater levels of detail and produce more accurate depictions of our thermal and geothermal stories. So that wraps up the work on phase 1 of this project, but we were of course still left with many questions. So I'll just briefly talk about what we are doing this winter to address the potential association of high geothermal gradients with subsurface New Brunswick evaporites. So geothermal gradients are typically given as an average, so an average increase in temperature per unit depth. but changes in geologic conditions in the subsurface cause average heat flows to increase or decrease over a unit depth. That can't be made into an average. So it's more accurate to say that the geothermal gradient is constantly changing through a stratigraphic column. So what we're going to be doing this winter is using the New Brunswick thermal conductivity, the New Brunswick rock thermal conductivity data that we collected in 2021 to more accurately calculate heat flows through each viable borehole column and determine the temperatures at the points of contact between each separate rock unit, and also to see how these results differ from or may differ from expected temperatures calculated using the average geothermal gradient. So this will hopefully help us determine where an individual rock unit might be acting as a heat conductor or a heat insulator. So we are excited to work on this project in this next phase. And so that's all I wanted to say for the presentation. Thank you very much for your attention. I look forward to answering any potential questions you might have. But for now, I will just stop sharing my screen and pass the presentation control back to Adam.
Excellent. Thank you very much, Joseph. Great job. I'll just put a little bit of a wrap on the presentation, and then we can proceed to the Q&A. I'll just share a quick outro slides. Here we go. Perfect. So a lot of information thrown at you today. I hope you found it interesting and helpful. There are some rich resources available at our website, C-Therm.com. In particular, the webinars tab. You can scroll back through numerous previous recorded webinars, including this one, if you would like to review this content again. If you want to share that with any colleagues or friends that you think would have interest in it, we'd certainly be grateful and encourage that. There's a great tech library as well, where we update any publications that are coming out referencing use of this technology, where thermal conductivity is referenced. This is searchable by keyword. It also has a good index on the different methods and where they've been applied. These are short summaries and links back to where the copyrighted peer-reviewed publications are available. So it's a good way to, if you're wondering, okay, great, I'm interested in this, but with a little bit different application, are there any peer-reviewed publications or anything I can find out there that might speak to it? This is a great place to start in terms of the search. If you're in a situation where you've been looking at this for a while, you know that you need to measure thermal conductivity, or you're looking to improve your measurement of thermal conductivity, and you're wondering what a potential next step might be, please feel free to use the chat box. We'll drop in some links of how you can book a video demo session with Aria and members of our team to see what this looks like in action. Pre-COVID, we used to come on site and bring a system. That's not very easy to do these days. So what we have put a lot of energy and investment in is setting up a demo facility with a library of materials. We have geological materials, for example, that we can pull and show you what this looks like with a live view. We've got a few different camera angles set up so you can get a bird's eye view of the sample setup, as well as screen sharing on the software and so forth. So it's a great immersive experience in terms of understanding what it is like to actually run a measurement. We can possibly also run a complementary sample test if that's something that's of interest in evaluating feasibility for this. If it's a more involved analysis, we would also refer you to our Thermal Analysis Labs group, TAL. They offer contract testing services that can be of support as well. And a portion of those contract testing fees can be applied towards purchase of a system, if that is something that is of interest. So it allows for kind of a gated adoption process where you can apply some of that equity credit. Ultimately, if you're just looking for a quote, we can provide that too. There's a form there for request a quote. We can get you a quick quote back within a very short time. So if you just want to get some budgetary numbers for your next capital budget cycle, we can certainly help you with that as well. We will be launching a series of upcoming application webinars in the next couple of weeks. So watch for that announcement shortly. There will be some on looking at polymer composites. We'll be featuring application work on electric vehicles, looking at all kinds of different areas of application for thermal conductivity. We'll have some guest speakers involved and be generally trying to drive awareness on issues related to thermal conductivity and optimizing the measurement of samples in different applications. Okay, at this point, I want to say thank you very much to all involved, Igor for setting this up, Aria for helping us out with the presentation, Joseph, who did a fantastic job both in the research and in presenting those findings and really talking to why thermal conductivity data is important in this area of application in geothermal. I want to also thank Dave Keeley, Dr. Keeley up at UMB was instrumental in setting this collaboration up with Dr. Bateman from our side. So I want to thank them both. They're on the line with us and very much appreciate, very grateful for their efforts in helping support this endeavor. Okay, with that said, I think we'll bring the formal presentation to a close. I want to say thank you to the audience for participating. If you'd like to stay on the line for the Q&A, please do so. We'd certainly look forward to picking that up there. And if you're going to drop off here, I wish you a wonderful day. Thanks, everyone. We'll be in touch. Q&A to follow.